In problem 44, we're going to use this table called an activity series to predict whether a redox reaction is going to occur or not. All right, so in A, iron metal is added to a solution of copper nitrate. So we need to know, is copper metal, right, the only thing metals do is lose electrons, going to lose electrons to copper 2 ion? So these are the reactants. Copper 2 nitrate reacting with iron. Copper 2's got a +2 charge, iron's got a 0 charge. So will iron give up electrons to copper 2? So this is when we refer to the activity chart. The way this is laid out is on the left-hand side, you've got the metals, right? Starting with lithium, going down to gold. At the top of the chart, these are the easiest ones to take electrons off of. As we know, they're alkali metals, right? So lithium, potassium, barium, calcium, sodium. As we go down, it gets harder and harder to take electrons off and eventually get to gold, which is a good thing. It's hard to take electrons off of gold, otherwise it wouldn't be a very good thing to make jewelry out of. On the other side, starting with gold 3+, this is the best taker of electrons. So going up the chart from gold 3+ up to lithium plus, you become a worse and worse and worse oxidizing agent. So the best oxidizing agent, the best taker of electrons is gold 3+, and the best giver of electrons is lithium. So the way this works is a reducing agent, right? Something giving electrons will give electrons to the cation below it on the chart. So iron is above copper 2 on the chart. So copper 2 will take electrons away from iron to become copper metal. So this reaction is going to go forward. Copper 2 will take electrons away to become copper. Once the electrons are taken off of iron, you get iron 2. All right, looking at the next one. So copper 2 is reduced. Iron is oxidized. All right, looking at the next one, zinc metal giving up electrons to magnesium 2+. So the question is, will magnesium 2+ take electrons away from zinc? Well, looking at the chart, as we know, magnesium is one of those reactive alkaline earth metals, right? It's easy to take electrons off. That means you're making something magnesium 2+, which is not a very good taker, right? If it's a good giver of electrons, you're making something that isn't looking very hard to take the electrons back. So magnesium 2+ will not take electrons away from zinc, which holds on harder to its electrons than magnesium does. So this can be a no reaction. You put zinc in magnesium sulfate and nothing's going to happen. Will hydrobromic acid take electrons away from tin? So it's a question of, will H+ take electrons away from tin? And the answer is, they got the wrong one there. We should be looking at it in terms of, later. We should be looking at it in terms of H+ ions taking electrons away from the tin. So will H+ take electrons away from tin? Yes. All right, so it must be that H+ lies below tin on the chart. Will nickel 2 take electrons away from hydrogen? No. Will cobalt 2+ take electrons away from aluminum? Yes. All right, so aluminum will give up electrons to cobalt 2+ to form aluminum 3+ and cobalt metal. So that's how you use the activity chart. It's a way of checking to see whether the reaction is going to occur or not. Do I have a strong enough oxidizing agent to take electrons away from a reducing agent? All right, in problem 16.1, we're introducing this new derived unit, molarity. Molarity is a unit of concentration. How much solute do you have dissolved in the particular solvent? So if I have 1.75 moles of zinc chloride dissolved in exactly 150 milliliters, what's the molarity of the solution? Well, molarity is moles per liter. So they gave me moles, right? I have 0.175 moles of zinc chloride. What I want to do is divide it by liters. So I've got to convert milliliters to liters and then divide liters into moles, and I get the molarity of the solution, how concentrated the solution is. There's other concentration units, but molarity is one of them, right? How many moles do you have dissolved in a liter of solution? All right, so like all ratios, right, moles per liter, this is a conversion unit. It's a way to go from moles to liters or liters to moles. So how many moles are present when I have 35 milliliters of a 0.45 molar solution? So like all unit conversions, you start out with what you're given, right? 35 milliliters of the solution. And then we can use molarity. I want liters in the denominator, moles up in the numerator. And in this way I can convert by multiplying, right? I can convert liters to moles by knowing the molarity. So when I multiply across, liters cancel. And I can figure out how many moles of nitric acid I have in 35 milliliters of solution. Looking at C, how many milliliters of 6 molar sodium hydroxide are needed to provide 0.325 moles of sodium hydroxide. So with this problem, I'm given moles, and I want to find milliliters. So I use molarity, I use the inverse of molarity, right? I want moles down in the denominator this time, and liters up in the numerator. So when I multiply across, moles of sodium hydroxide will cancel. They want it in milliliters, so we convert from liters to milliliters. So moles cancel, liters cancel, and I've converted to milliliters using molarity. All right, problem 69. Which will have the highest concentration of potassium ions? 0.2 molar potassium chloride, 0.15 molar potassium chromate, or 0.08 molar potassium phosphate? So what we need is a conversion factor to go from moles of the ionic compound to moles of potassium ion. So we look at the formula for that. According to the formula, for every 1 mole of potassium chloride, you're getting 1 mole of potassium ion. For every 1 mole of potassium dichromate, I'm getting 2 moles of potassium ion, right? According to the subscript. For every 1 mole of potassium phosphate, you're getting 3 moles of potassium ion. So using this conversion factor, I can go from moles of the ionic compound to the moles of the ion I'm interested in. So we just have a new conversion factor here. So when I multiply across, moles of the ionic compound cancel, and I've converted to moles of potassium ion. So it's potassium, 0.15 molar potassium chromate that has the highest concentration of potassium ion. All right, looking at part B, we have 30 milliliters of a 0.15 molar potassium chromate solution, 25 milliliters of a 0.08 molar potassium phosphate solution. All right, so let's convert to, milliliters. Convert to liters, so we can use the molarity of potassium chromate to convert to how many moles of potassium ion I'm going to have. So I looked at the formula to figure out how many moles of potassium will be liberated when potassium chromate goes into solution. And there's my conversion factors, right? Everything cancels except for what I want, moles of potassium ion. Do the same for potassium phosphate. Convert to liters, convert to moles of the ionic compound, convert to moles of the potassium ion, and when I multiply across, we see that my 30 milliliters of my 0.15 molar potassium chromate solution is going to have the most moles of potassium ion. All right, problem 73 is a dilution problem, right? You have a concentrated stock solution, and they want to know how many milliliters of this solution should you dilute to make 1,000 milliliters of a 0.25 molar ammonia solution. So we're using that formula. M1 V1 is equal to M2 V2, right? My initial concentration times my initial volume is equal to my final concentration times my final volume. So I plug in what my final concentration is going to be, 0.25 molar. My final volume is going to be 100 milliliters, which is 1 liter. So it's got to be in liters, right, if you're using moles per liter. And my initial concentration is 14.8, so that's concentrated. So what I'm solving for is my initial volume. How little, what little bit of my concentrated do I have to start with to dilute up to 1 liter to get a 0.25 molar solution? So I rearrange it, right? Get V1 by itself, divide both sides by 14.8 molar. When you divide molar by molar, it cancels, and I'm left with how many liters? So I've got my liters, right? I've got a fraction of a liter here. It'd be more convenient to put it in milliliters. So we convert it to milliliters. So I have to start with 16.9 milliliters of my concentrated and then add water to it up until I got to 1 liter to get a 0.25 molar solution. I mean, that's how you read this. That's how you look at it. We're diluting solutions. All right, so looking at part B. Again, we're going to be using M1 V1 is equal to M2 V2. We've got 10 milliliter portion of that stock solution, and we're going to dilute it to 0.5 liters. What will the final concentration of the solution be? So the way this problem is phrased, that you know what the initial concentration is, right? It's the stock solution, and you know how much you're starting with, right? Or your volume you're starting with, 10 milliliters. And you're going to dilute up to 0.5 liters. So what's my new concentration? So I isolate M2 by itself by dividing both sides by the volume. When I divide liter into liter, a liter cancels this time, and I'm left with my new molarity. All right, so I've diluted it down to 0.296 moles per liter. So that's how dilution problems work.